Hey folks, welcome back. Let's talk about light and review the things that you learned about light in terms of the math from first year chemistry. So just to start, light is an electromagnetic wave. And that means that the wave consists of both an electric field and a magnetic field that are oscillating orthogonal to the direction of travel of that light. So as I look at the diagram at the top of the screen, if the light is traveling to the right in this direction, then the electric field and the magnetic field are oscillating perpendicular to that. And when we take a look at light and we think of it as a wave, then we can talk about the wavelength of that light. The wavelength is the distance between two repeating points on a wave, and typically we'll use crest to crest, that's typically easiest, but it doesn't matter, any two repeating points. And the symbol for wavelength is the Greek letter lambda. As wavelength is a distance, our units are going to be meters, or often when we're talking about visible light, we'll talk about nanometers. 1 nanometer is 1 times 10 to the negative 9th meters because visible light has a very small wavelength. When we do calculations with this, we're going to see that we need to use meters, but you can convert between any unit of length when we talk about wavelength. Wavelength is one way to describe a wave, but we can also talk about its frequency. So frequency is how quickly the wave repeats itself. It is how many cycles per second are occurring. Now the symbol for frequency is the Greek letter nu. And although its units are formally 1 over seconds, how many cycles happen per second, we will typically use the unit hertz, which is just 1 over seconds. And when you look at a wave, there is a relationship between the wavelength and the frequency. As you have a longer wavelength, the frequency is lower, so that frequency of oscillation is slower. In a in a shorter wavelength situation, the frequency is going to be higher. And there's a mathematical relationship between these two and the rate at which that wave is propagating. And this is the equation used in first year chemistry, C equals lambda times nu. C is the speed of light, and that is 2.998 times 10 to the 8th meters per second. It's on the AP equation sheet. And that's going to be equal to the wavelength multiplied by the frequency. Now, because the speed of light has units of meters per second, in order to use this equation, all your units have to match. And so as we've seen so often, you need to use meters for the wavelength in order to have the same units on the left and the right side of this equation. And your frequency is going to be in hertz or inverse seconds. And that way the units are the same left and right. When you look at the electromagnetic spectrum, we have a range of different types of light, and they're all electromagnetic waves. What differs is their wavelength and their frequency. So on the long wavelength, low frequency side of things, we have radio waves. On the other side, where we have very short wavelengths and very high frequency, we have gamma rays. It's worth pointing out that in the electromagnetic spectrum, we have gamma rays, X-rays, UV, visible, IR, microwaves, and then many different variations on our radio waves. Visible light, the part that interacts with our eyes, is a very small sliver of this. And so as we talk this year, we're going to talk about how each of these different types of light interacts with the matter around us and what we can use them to learn about that matter. So light is a wave, but it's also a particle at the same time. Always light and a particle. And depending on how you set up your experiment, you can see and show both that light and that wave-like property. And we'll talk at school about the experiments that confirm that it is both a wave and a particle. But for here, let's talk about what we can use that particle-like behavior to learn about our light. So a particle of light is called a photon, and this is kind of the little smallest chunk that light comes in. And if we talk about the energy of that photon of light, we have a way to compare the energy content of all the different types of light that we've seen. And so there's an equation for this. E equals h nu, where E is the energy of your photon of light. one photon. H is Planck's constant, and nu is the frequency of your light. So as we look at this equation, Planck's constant is a tiny number, but that's because we're talking about the energy in a single photon of light. And typically on a daily basis, we have moles and moles of photons hitting at any moment in time with any surface. So Planck's constant is 6.626 times 10 to the negative 34th joules times seconds. Frequency has units of inverse seconds or hertz, and so our energy is going to come out with units of joules. For each photon of visible light, or really any light, that's going to be a very small amount of energy. And so you can expect to see 10 to the negative 19th, 10 to the negative 15th for your exponents. When we talk about the energy of a photon, we can also relate that back to the wavelength and the frequency, because these two equations allow us to interconvert between energy, frequency, and wavelength. So we can also talk about the different types of electromagnetic radiation in terms of their energies. If something has a very large energy, then it's going to have a very large frequency because those are directly related. But it's going to have a very small wavelength because frequency and wavelength are inversely related. On the contrary, if something has a very low energy on the other side of our spectrum, then that means it's going to have a low frequency and a very long wavelength. And you need to be able to go back and forth between energy, frequency, and wavelength using these two equations so that we can talk about the different types of light. And then we'll take that and talk about how it interacts with our matter.